So I'll ask you questions like do the left, then do the right. And the beautiful thing, like I said earlier, is most of the work you did for the left ones are going to show up again down here. It's crazy. So it's not doing completely all over again. So here, every width every width is 1/2. What's the height of the first rectangle is going to be f of 1 plus the height of the next one is f of 1.5. And then I just keep on adding a half until I get to 4. Well, until I get to 3.5, sorry. 1, 2, 3, 4, 5, 6. 6 rectangles. Yeah, I do that because I've made this mistake. It's easy. We're humans. We're going to make mistakes. Just do a quick check. I've only got 6. Thank God. I'm only supposed to have 6. Because you will get into that pattern. You go f of 4, f of 4.5. Wait a minute. I was supposed to stop at 6. Check. And now you just got to, throw all that shit in here. Right? Now, just to remind you guys here, this is beautifully set up for this. Let me show you something really, really nice in here. Negative x squared plus 6x minus 4. There's two kind of ways to do this. Let me show you the more direct way to do this. Well, I'm not going to show you the other because it's kind of convoluted. So if I do table, how much of you guys ever played with the table? Go to the table right now. It's not really what I want. So I can go to table set, make it start at 1, right? And make it change in table to be a half. Now it's going to match up. Now I can see, get out of there, graph. There's the graph. All right, go away. Table. Now I've got all the values I need. Kick ass, right? I know you know how to plug something into a function and blah, 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 blah. There's got to be a shortcut to get through that. So now I've got 1/2 times 1 plus 2.75 plus 4 plus 4.75 plus 5 plus 4.75. Bam. 1, 2, 3, 4, 5, 6. Is somebody cool with that? It's just a shortcut to do that step where you have to evaluate the function at those points. That will always work because the width will always be the same for us. Can't like it. And then whatever the hell that all is. Let's see. Did we do that yet? You're like, I didn't know what to do. Let's see. Let's see if I plunge that all in there. Right? Yep. So I get 11.125. That's what I get. Please let this be not that bad. We're finding areas of rectangles at the moment. That's like, what the shit? We were just doing Newton's method, and now we're finding areas of rectangles. It's beautiful. Enjoy it while you can. 11.125. That's my estimate using left endpoints. Now, right endpoints, I really want you to realize. To draw the picture now, it's going to be, so let me put this back in here. 1.5, 2.5, 3.5. So to draw the picture, the height's going to be based on this side. See how I do that just to make sure? So wherever it's based on, that's where I draw from, and then over and down. Cool. So the picture, how are we doing? So it's using right endpoints. You guys okay? Okay. Some of you guys have a look like you want to ask a question, but you're not. So, okay. All right. And so what's this really going to be? How's this going to look for this now? It's going to be 1/2 still. And instead of starting at f of 1, it's going to start at f of 1.5, and it's going to go all the way to f of 4, because f of 4 was the height of this last one. So it's going to have a lot of repeat values, right? So it's going to be 1/2 f of 1.5 plus f of 2 plus f of 2.5 plus f of 3 plus f of 3. Yeah. F of 4. 1, 2, 3, 4, 5, 6 rectangles. So it's going to be 1/2, this, and then I'll bet you f of 4 is this, because of symmetry. And again, if you don't trust me, you can put it in there. So we get, so I'm going to start here, because I didn't start, now I start at f of 1.5. Please see how this is so nice. 2.75 plus 4 plus 4.75 plus 5 plus 4.75 plus 4. So some of you guys might realize how I'm not adding that 1, but I am adding this 4, so it's 3 bigger than it was. So the answer is 3/2 bigger than this. So that should be 12.625. Let's see if I'm right. So really, to do this, I can just redo this, and in place of 1, I could put 4. 12.625, kick ass. If you don't understand the shortcut I did, it doesn't matter, we're shit. You just do this, and you'll be fine. Why was this an under? Do you see how that's less than this? But can't you, I could have, I was thinking about it, and I didn't. From the picture, can you see that it's going to be an underestimate? Because my rectangles more often are under than over. This one's going to be an overestimate because it's the exact reverse. So in general, now this one we did earlier was 20 and 20 on both sides, just because of the way the function was. But here, how do I immediately make a much better guess? I just average these two. So if I average those, what do I get? 23.8, so I get 11. I'm going to go and say 11.9, I think. Is that what you get? Anybody do that yet? What is it? 11.875? Probably oversimplified things. Yeah, I did. Oh, I left off the 5. Okay. So 11.875. That's my best guess using 6 rectangles. So I underestimated with left endpoints. I overestimated with right endpoints. So hopefully it makes sense that in general what we do is we average those two. And then let's see what the actual answer is. I've got the function in there. Let me graph that bad boy. I got it graphed. And then I can calculate the infinite sum. Let me let the rectangles go to infinity from, what was it? I forgot already. 1 to 4. The answer is 12. Would you say that's pretty good? For just 6 rectangles. Now again, that function is unbelievably nice. So the worse the function is, the more rectangles it takes to get a decent approximation. So we got 12 from the calculator. How are you guys feeling about this? The basic idea of covering an area with rectangles, finding the areas of those rectangles, get a feel for the area of that under that function. That should hopefully be very straightforward. And then the work for a finite number of rectangles is remarkably straightforward. And some of you guys are like, yeah, whatever, man, for you. This really isn't that horrific. Let me give you this. We're not going to, let me talk a little bit about what this says. And actually, before I do that, let me show you one thing. Any questions from this? By the way, I don't think anybody had a question. Okay. There are urban legends in mathematics. None of them would make a very good movie, but there's an urban legend about Gauss. Anybody ever heard of Gauss? There you go. If you took statistics, you did normal curve is actually more commonly called the Gaussian distribution. It's a little more general idea. Gauss is also how we measure magnetic field strength. So for a mathematician to have a unit of measurement named after him, that's like the ultimate, like, holy shit, you made it, dude. You can now die and rest in peace. Which is what he did. He's not still around freaking us out. Where's my best bet? You are. So watch this. It's kind of cool. There's this urban legend that says the teacher was getting upset about the students. They were all kind of blah, blah, blah. So the teacher said, okay, sit down and add the first 100 integers, or 100 numbers, the whole natural numbers. 1, 2, 3, up to 100. Add them up. So he sat down and started reading his newspaper. He's like, yeah, that shut him up for a while. Gauss, little smart-ass Gauss, 10 seconds later, he's up there saying, here's the answer, teach. I'm going to start throwing shit again. It's like, all right, shit. So the teacher's like, what? And the teacher sat down and did 1 plus 2 is 3, plus 3 is 6, plus 4. So, about 3 minutes later, the teacher's like, yeah, your answer is correct. What? And then, of course, they probably thought he had demons or something. I don't know. You must be taken. You guys kind of with me? It's a little different back then. So the shortcut, I don't know, somebody might have seen this before. Maybe, no? So really, what this is it's the sum, I equals 1 to 100 of I. Think about that. So when I is 1, I get 1, plus I is 2, I get 2, plus I, all the way up. So here's what Gauss realized. What's 1 plus 100? 101. What's 2 plus 99? How many 101s am I going to get? How many pairs of 101s? 50. So there's going to be 100 divided by 2 pairs, and every pair adds up to be 101. You do like this. Okay, so 1 plus 100 is 101. That sum is going to be repeated 50 times. So this is a cool idea by itself, but look what the answer came out to be. 50 times 101 is 50-50. So the sum of the natural numbers from 1 to 100 is 50-50. That's, by itself, that's kind of nifty. No? And that rhymes with 50-50. So hey, I'm a poet and didn't realize it. What does this look like visually? What does this look like in formula form? So the sum, I equals 1 to n of I, is going to be n over 2, that many pairs, times the first one plus the last one. That's the repeated sum. So no matter what n is, that's going to be the result. So I'm going to bring, if I remember, so I got this guy we just did. Let me write it in its more natural form. That's the same thing. Is that cool? And we're also going to look at what about this guy, and we're also going to look at what about this guy. Right? If I remember next time, I might bring the proofs of these. Unfortunately, there's a form of proof called mathematical induction. Has anybody ever heard of mathematical induction? Sometimes some crazy pre-calc teachers do it. If you take Calc 2, you definitely will do it. There's not enough time for us to do it in here, but that's the way I would prove these next two would be through math induction. So sometimes students are interested, so I bring copies of the proofs. So I'll do that next time if I remember. These are what will show up when I do what we just did with infinite rectangles instead. I will get, like, this will show up in the middle of my work. So what can I put there? This. This will show up, so then I can put whatever the answer is there. I can replace it with that. And why is that nice? Because then I'm letting the limit as n go to infinity, and I can evaluate that then. So we'll see that. Let me give you this, just in case you're... Did I give you this yet? No. We're going to do this handout next time, but I want to give it to you just so you can look at it if you want to get a little preview. This for me is very colorful. There's like two colors, black and blue. This might be how you feel after a class. So section 5.1 is finite number of rectangles. Section 5.2 is infinite number of rectangles. Oh, I forgot them right there. So there's that one. And then you can see in the little box down there, you can see the one for I squared and the one for I cubed. Look how the one for I cubed is related to the one for I, which is nifty. But you would never guess it. I would never guess it until you do the actual proof. Okay. I think that's plenty for today. So we're going to do 5-2, and then what we're going to do is try to relate the area under a function with the antiderivative. If those were somehow related, I wouldn't have to do all that shit anymore. So really, this is sort of like when we learned the limit definition of derivative, and then we finally learned the shortcuts. So this is sort of the, when I bring the limit as n goes infinity, it'll be the limit definition of what's called an integral, which is the area under a curve using the antiderivative. The limit definition, and then we're going to start just doing straight up antiderivatives and doing the shortcut. That's what's going to be next. And that's plenty. So I'll see you guys Thursday. Yes.
About so can I know why the from that left point, why would it be from the F1 and the right end?
So how tall the first rectangle has to be from 1 to 1.5 because the width is a half.
Yeah.
And they start at 1, right? How tall is it going to be if I use the left end point? It'll be this tall.
Yeah.
Well, how tall is that? F of 1.
Yeah.
How tall is this going to be? F of 1.5.
Oh, okay.
So if I take the height times the width plus the height times the width, that's the adding up all the areas of those rectangles, and I end up with an approximation for the area under the curve from 1 to 4. Now it was a little bit under because these rectangles don't fill it in very well. That's why I was under. This one was over because these rectangles went too far. So when I averaged them, I got something really close to the right answer.
Can I see that?
Yeah.